Hi, my name is Kirill. In this video, I will present our work on theoretical guarantees for learning with inconsistent surrogate losses. In this paper, we consider the standard structured prediction setup where the task is to predict structured objects like pixelized masks for image segmentation or character sequences for OCR. We extend upon the recent framework by Asaken et al., who provided bounds on the number of samples needed for the learning algorithm to get a generalization error within epsilon of the optimal. We go beyond the previous works and provide learning guarantees for inconsistent methods, and prove that they can lead to efficient learning at the cost of a limit on the best achievable generalization error. First, I'll review the standard structured prediction setup. To predict, we compute a score fy of x for each possible label y and output the label with the highest score. We measure the prediction quality by a loss function L, which compares our prediction and the ground truth label. The goal of learning algorithm is to find a score function f that minimizes the generalization error, which is the expected loss of the prediction, usually called actual or population risk. Usually, the expectation is non-convex in f, and thus optimization guarantees are not available. A typical solution is to minimize the expectation of a convex surrogate function phi, which is surrogate risk. With the proper choice of phi, this process implies minimization of the actual risk as well. For example, the conditional likelihood, structure, hinge, and quadratic losses are popular surrogates. We capture the connection between the surrogate and the actual losses with the calibration functions. The calibration function says how accurate the optimization has to be on the surrogate risk to give a guarantee on the actual risk. Consistency means that the exact optimization of the surrogate risk always leads to the exact optimization of the actual risk. In terms of calibration function, a surrogate risk is consistent if the calibration function is greater than 0 for all positive epsilon. The calibration function also provides learning guarantees if combined with the optimization convergence rates. For instance, the number of steps of online SGD required to obtain an upper bound on the excess of the actual risk is proportional to the inverse square of the calibration function. Recently, several papers derived generic lower bounds for quadratic surrogates that were quadratic in epsilon and tight for some losses. The constant C depends on the choice of score function family. One of the key insights of Asaken et al. Was that imposing structure upon the score function family helps to achieve efficient learning. For example, adding appropriate score structure for ranking with mean average precision loss gives you exponentially faster learning. At the same time, putting restrictions on score functions can lead to inconsistent surrogates for which only trivial lower bounds were available. Our main result is a generic non-trivial lower bound for the inconsistent case, which is a truncated quadratic function shifted to the right. This result shows the trade-off between the level of consistency and the learning speed. Apart from the learning speed, inconsistent settings can be preferable in practice for other reasons. In the ranking example, the consistent setting requires solving the quadratic assignment problem at the test time, which is NP hard. The inconsistent setting allows to predict with sorting, which is much better. For the details, please check out our paper.